To measure is to compare and quantify things in the real world. For example, kids will see who is the fastest or the longest, and in that way they measure. But to measure in that way, you don't have to know what the meter, kilogram, or second is. But often you want to quantify things. For example, say that the length of a pen is 3 erasers long. And if you have the length of the pen that you call a quantity, and say that it's 3 erasers long, then 3 is the number, and erasers long, that's the unit, how many erasers you have. So you can quantify in this way. In principle, you can measure all length using this eraser as a unit. For example, you can say that the book is 9 erasers long, or the height of the room is 100 erasers tall. But if you live in Norway or Sweden and want to measure things in the USA, then it's very impractical to send the erasers back and forth to measure in that way. So what you will need is have some local unit. And this is also in the principle how it works in real life. But instead, of course, using eraser, you have some standardized unit. And that means that it's not dependent on time or where in the world you are. For example, a meter, that's a standardized unit. And the length of the meter is, of course, arbitrary. But the length of the meter is part of the SI unit system, a standardized system of units. And the eraser, for example, that's an example of a non-standardized unit. So we have the SI system, that's a standardized system of units. For example, we have the meter, that belongs to that. The kilogram. Actually, it's a kilogram that is the unit here, not grams in the SI system. And then, for example, a second. And there are more units, but these are some examples. Historically seen, you have a prototype meter and the prototype kilogram, but the modern definitions try to get away from these and define them in more ways that it's easier to not to be dependent on a prototype. And then we talk about here a kilogram, and that is an example of a prefix. For example, you have the kilo. That's a prefix, and you often just write it as a K, and it means 1000 or 10 to the power of 3. And then you have, for example, milli. You can talk about the millisecond or millimeter or milliliter. You write that as an M, and that's 10 to the minus 3. So these are just letters, shorthand for numbers in terms of 1000 and tens and so on. And you have a whole list here. For example, we won't write the complete list here, but we'll come back to more later on. But for example, if you have a mega, that's also a prefix. You write a big M, capital M, and that's 1 million. And another example, centi. A centi, that's 10 to the minus 2, that's a 100th. Or a deci, that is 10 to the minus 1, a tenth. So these are prefix. These can be combined with units. For example, you can talk about a millisecond, and that of course means 1000 of a second, or 0.001 second. Or you can talk about a kilogram or kilobyte in computer units. So it means kilobyte. And so on. So you can combine units with prefixes to make suitable units. And now you can convert between units, or you can calculate using units. For example, if you say that a book is 7 erasers long. Okay, so you say that the book is 7 erasers long. And for example, if you have a house, and the width of the house is 50 books Then of course you can express now the width of the house in terms of erasers. So you just have 50 times 7 erasers. So 350 erasers, for example. So this you can calculate in terms of non-standardized units. And also, for example, you can convert between, if you have yards, and convert back and forth to meters. But we will now mainly look at the SI system and the prefixes that goes along with it. So let's look at lengths to start with. And we'll look at that in the SI system, the metric system. So we have a 1 meter that is 10 decimeters and 100 centimeters and 1000 millimeters, for example. We can also have, if you talk about not the lengths, but if you talk about liters, we have a similar fashion here. 1 liter is 10 deciliters, 100 centiliters, and 1000 milliliters. So you see that these transformations between units has nothing really to do with length. It has more to do with the prefixes. So deci, centi, and milli. And now you can also go the other way around. For example, if you have 1 decimeter, you can convert that to meters. So a decimeter, that is 1/10 of a meter. So 0.1 meter. Or for example, 1 centimeter is 1/100th of a meter. 0.01 meters. Or let's say that you want to convert between kilometers and decimeters. Then you first can go to meters. So this is 1000 meters, since kilo means 1000. And then a meter, that is 10 decimeters. This becomes 10 to the power of 4, or 10,000 decimeters. So in this way you can transform. You can of course also transform in the other direction. For example, if I have a centimeter, and let's say I want to transform that to a kilometer, then I can first write it as 0.01 meters. And how many kilometers are there in the meter? It's just 1,000 of a meter, of a kilometer. This is this. And they multiply these. Or more practically, so 1, 2, 3, 4, 5, 10 to the minus 5 kilometers. Or let's say that you want to transform between, if you have 7 centimeters, and you want to write that in terms of decimeters, then you can write this as 7 times 0.1 decimeter. Of course, a centimeter, that's 1/10 of a decimeter. This just becomes 0.7 decimeters. The area is a measure of how large a surface something has in a plane. Or you could talk about also the surface of a sphere. So that's the size of an area, size of a surface. So for example, if you take a square, and let's say that this is 1 meter, and this is 1 meter, then per definition, this has the area unit of 1 square meter. And that you write as m squared. And we'll come back in a moment why you write like that. But let's just see here that what will be the area then of a rectangle. Let's say that we have 3 meters here and 5 meters here. Then we see that we can divide it up into squares. So let's measure in terms of these squares with sides 1 meter. So we can quantify the area in terms of square meters. So we just see how many of these will fit here. Okay, now it's not drawn to scale, but so let's divide them up into square meters. So now we're only making a rough sketch. So let's say that all of these are now squares and equal sizes. Okay, so how many are there? Of course, in this direction we have 3, and here we have 5. So we can just count 3 times 5, this many square meters. So this is 1 square meter. So 15 square meters. So let's make a measure of area. So let's say that this more generally has a side length of A and this B. Then we can define the area of a rectangle as A times B. And this will work out nicely because now the area is proportional to both A and B. So if you double A, then the area will double. If you double B, the area will double. So it has the right property. And what will happen now, for example, if I take these 3 and 5, then I have 3 meters, or it was opposite, 5 meters times 3 meters. And let me now treat this as all of them are numbers. You can look at the unit as like a variable, an unknown number. So you just multiply them in any order. So you just treat them as numbers. Then I will get this. But here we see, this is just m squared. So this becomes 15m squared. So you see the reason for calling this m squared, this symbol. This is a symbol for the area here. It comes out naturally if you define area as this. Similarly, we can define units like, for example, square decimeter. That's just a square with the side length of decimeter, 1 decimeter. So for example, now we have the area 1 square meter. How many square decimeters is that? Then we just have to draw a figure. So we have here square meter. So this is 1 square meter. But how many square decimeters can we fit? In each direction we can fit 10. So you can fit 10 decimeters in 1 meter. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And also in the other direction we can fit 10. I won't do them all here, but so we have 10 times 10. And these squares here, this is a square decimeter. So you just to count 10 in that direction, 10 in that direction. So we have 10 times 10, 10 times 10 square decimeters. So 100 square decimeters. So it's easy just to count, draw a figure and count. And then of course we can turn this around. Now I know that 1 square meter is 100 square decimeters. So I can just turn it around and say that 1 square decimeter is 1/100th of a square meter, or 0.01 if you like. But we also saw that we could treat units as numbers. So let's for a moment calculate it as it were numbers. So if you have a square meter, you can just write as meters times meter. And the meter, what is that? That's 10 decimeters. And here we can multiply them in any order. So we have 10 times decimeter times decimeter. So this is 100 square decimeters. So you see that we arrive at the same result as here. So we can just calculate with units in this way. So we have that 1 square meter is 100 square decimeters. Note that here we have written like this. This should not be confused that you have a multiplication sign here. It's not deci times square meters. Instead it is the square of this one. So it's decimeters times decimeters. But instead of writing like this, we are a bit lazy and just write it like this. So this means this. So we can convert between area units in that way. Let's take another example. For example, if I have 5 square centimeters, I want to convert that to millimeters, square millimeters. And this is centimeter times centimeter. Of course I could draw a figure also, just figure out how many square millimeters. But let me count instead with the units. So it's 5. And the centimeter, that's 10 millimeters. So this is 500 square millimeters. Or if I prefer, or if I want instead to convert this to decimeters, for example, then again I can write it as this. And then we have that the centimeter is a tenth of decimeter. So centimeter is a 0.1 decimeters. So this is 0.05 decimeters square. So here I'll just multiply the numbers and then multiply the units. Or you could instead, of course, use the figures and divide them up into squares and just count. And similarly we have for volume. So volume is a measure of how much space there is inside some object. For example, if you have a glass of water, so if you have a glass of water, so much space does this occupy, this water in the glass? Or something else, you can have some random shaped object. So how much space does it occupy? Then you talk about volume. And how can you quantify volume? You can, for example, then make cubes. So if you have a cube, so let's say I have a cube of 1 meter, side length of 1 meter. Then per definition, the volume of this is 1 cubic meter. And they write it like this. So for the moment, this is just a symbol for this. So this is the volume of this cube. So you say it is 1 cubic meter. Okay. So for example, if you have some box, you have a box now you want to find out how many cubic meters can you fit in this. So let's say that this is 2 meters, this is 5 meters, and this is 3 meters. Okay, so how many of these cubic meters can you fit inside here? Again, it's not drawn to scale, but you see that in this direction you can fit 2, and in the lengthwise you can fit 5. So I'm making a very rough sketch here now. And in this direction you can fit 3. So you see that you just have to count 2 times 5 times 3. So just multiply the numbers, quantifying the length here. So this many cubes, 1 cubic meter can you fit. So the volume of this object is this. So 1030 cubic meters. So you just have to multiply, just count how many of these cubes you can fit. More generally, you can define a volume. You define a volume of a box type, like a box of that type, as A times B times C. So let's call that A, this B, this C, more generally. So you just define volume as multiplying the lengths. And then it will work out correctly, because now the volume is proportional to each of these side lengths. So for example, if I double one of the side lengths, the volume should double. And what happens now if I just plug in the lengths? For example, let's say we're back now to this example. So 5 meters times 3 meters times 2 meters. Then again we have 30 if you multiply the numbers. Then we have meter times meter times meter if we treat the units as numbers we can count with. Here just have an example of m cubed. So since we have meter times meter times meter. And there we see a reason for writing the symbol like this and calling it a cubic meter, because if we treat the units as numbers we can count with, it will work out nicely. And if you have defined the volume in this way. And then we can convert between units, similar to how we did for area. So let's just quickly draw our cube here again, or sketch. So let's say we have a cubic meter here. So we have a side length of 1 meter. How many how many cubic decimeters goes there in 1 cubic meter? So how many cubic decimeters? Then we just have to count. We have to divide this up into cubic decimeters. We see that we can fit 10 in this direction, and we can fit 10 in this direction, and in this direction you can also fit 10. So just see how many. It's 10 times 10 times 10. So 1 cubic meter is 10 times 10 times 10 cubic decimeters. So 1000. So just see how many we can fit inside this cubic meter. Alternatively, you could also just treat them as units, numbers here as numbers. So we have that this is a meter times meter times meter. And just 1 meter, that's 10 decimeters. And if you multiply the numbers, then the units, this will become 1000. And this become a cubic. So we can just convert in this way also. Or let's say that we want to go from 1 cubic centimeter and transform that to cubic meters. So how many? And again, we just write the cubic centimeter as centimeter times centimeter times centimeter. And how many meters are in a centimeter? Is a 10 to the minus 2 meters. So this will be 10 to the minus 6 in total, and meters cubed. So we see here that 1 cubic centimeter is 1 millionth of a cubic meter. A common unit used for volume is liter. And what is a liter? 1 liter per definition is 1 cubic decimeter. So if you have a cube of side length 1 decimeter, the volume of that is a liter. And then you can just count with the unit liter in the normal fashion. For example, if you have 15 deciliters, here is deci, the prefix. Let's say that you want to write that in milliliters. Then deci means 100th, and a milli means 1,000. So we have that this is 100 milliliters. So deciliter is 100 milliliters. So this just becomes 1500 milliliters. So there's nothing special about the liter. You just calculate it with like any other normal unit. You just have to remember the definition. So 1 liter is 1 cubic decimeter. Then let us look at time. Yeah, what is time? Time is what we measure on the clocks, but originally we have several things in the nature that give rise to time, and it's things that are periodic. For example, the seasons and the Earth's orbit around the sun. That's a basis for time. So if you have the Earth, it's rotating around the sun. So if you have the sun in the middle, then we have that roughly the Earth rotates in a circle around the sun. And due to the tilt of the Earth, you take the axis through the poles, it tilts respect to the plane it orbits. So sometimes in this part, this half sphere of the Earth, this face will face the sun. So there will be on this part down here, we will have summer, and up here we will have winter. And here is the opposite. Here we are in the north, we are turning towards the sun, so here we have summer, and down here we have winter. So the tilt of the axis determines the seasons. So here we have winter, spring, summer, and autumn. And now, of course, we know that orbit around the sun, how many days does it take? Yeah, it takes 365 days, or to be exact, 365.24, or even more decimals. So that's 1 year. And what is a day? That's the time it takes for the Earth to orbit around itself once. So that's a day. So we have a day, and so a day is 24 hours. Some units here now corresponds to things in real life. For example, a year is quite natural since it's time for orbit the sun once. Our day is more like a cultural thing. It's just divided up the day into 24 hours. We could have divided up in any. So there are no natural reasons for having 24. And then we divide up an hour into minutes. So it's 60 minutes. And that's also just arbitrary, just had 60. There's nothing really in nature that corresponds to this. And each minute is 60 seconds. So we have like this. Okay, so we talk about months and years and days and hours and so on. A month, by the way, you have that the year is 12 months. So a month month has to do with the orbit of the moon around the Earth. And a month is, how long does this take? It takes 27.3 roughly days for the moon to orbit the Earth. So when we consider months as having different number of days between 28 and 31, that's also more cultural thing. For example, in the Jewish calendar, they have vary between 12 and 13 months. And some African cultures have a week is only 4 days. So some of these time measurements units of the time are more cultural, and others are corresponding more naturally to things in real life. And then you can talk about analog and digital time. So if you count the day in analog time, you just count between 0 to 12 hours. And then you repeat. So you say 12 a.m. or 12 p.m. Digital time instead, you talk about 24 hours. This is times 2. Since an hour, we transform between an hour and minutes, that's not given in terms of 10 or hundreds, but in terms of 60. So you have to be a little bit careful when you transform. For example, if I have 0.1 hour, how many minutes is that? It's not equal to 10 minutes, but rather it's equal to, so 0.1 hour, an hour is 60 minutes. So this is 6 minutes. So you should be careful when you're transforming like this. Or for example, if you have 1 hour and 30 minutes, that is not equal to 1.3 hours, but rather 1.5 hours. So you have to be a little bit careful when you transform between hours and minutes, and don't think too quickly. Then you can also talk about mass, weight, and density, or mass density. What is mass? Yeah, a mass is a measure of how much an object resists to be accelerated. So if you push on an object, if you have a huge mass, or if it has a large mass, then it will resist your push more, so it won't accelerate that much. A weight, on the other hand, in everyday life language, these two are synonymous, but they are not in physics and not in science, because weight has to do with how the gravitational force on an object. So if you have an object, it's pulled down to Earth due to gravity. So the weight is equal to the force it's pulled down due to gravity. That means that if you have an object on Earth or the moon, it will have different weights. So if you have the same object on the moon and the Earth, it will have different weights, but will have the same mass. So mass is independent where you are, but weight depends if you are close to a planet or freely floating in space. But if you stick to Earth, then these two could be used as synonymously because they are proportional. So as long as you stay on the Earth, that's fine. Then you can use these two synonymously. And both you can talk about in the units of kilograms. But strictly seen, weight is in units of newtons. SI unit for mass, that's kilogram, not gram. And there is a prototype mass if is stored in Paris. So 1 kilogram is the weight of, or the mass of that one. But there are also more modern definitions. And for example, we have 1 hectogram. hecto is a prefix meaning 100. So this is 100 grams. So this is 0.1 kilogram. But other than that, it's the unit for mass. We can just convert between units in a normal fashion using prefixes. And then let us just say that if we have a liter of water, the weight of that is 1 kilogram. That's the old definition of mass. So if you have 1 liter of water at 4 degrees Celsius, per definition that the mass of that one is 1 kilogram. Not according to the modern definition, but it's even according to the modern definition, this is very close. So you can use this in terms of weight or mass. What is mass density? Or just density? We will use the Greek letter rho for that. So this looks like a P, but it's more bent here. The definition of that is you have a mass of an object divided by the volume of the object. So mass density is how much mass there are per unit of volume. So if you have an object, so let's say this has a mass m and a volume v. So if you divide these two, you get the mass density. So for example, if this has a mass of 6 kilograms and it has a volume of 2 cubic meters, then the mass density is 6 divided by 2 kilograms per cubic meter. So 3. So this is SI unit for mass density, kilograms per cubic meter. So here I have a combination of several units making up the SI unit. For example, you have what is the mass density of water. Then we know that what is the mass of water. If you have 1 liter of water, it weighs 1 kilogram. And 1 liter, then that's the volume. So mass divided by volume. So here we have a kilogram divided by liter, but the liter is a cubic decimeter. And the cubic decimeter, that's 1,000th of a cubic meter. So this is 10 to the power 3. So the mass density of water is 1,000 kilograms per cubic meter, or 1 ton. One common thing to measure or use as units is currency. And you can convert between currency in the same way as you convert other units. So for example, let's say that you have a dollar. So I have a dollar that's equal to, let's take some number here. Let's say it's equal to 9 Swedish kronos. And then Swedish krona, let's say that that's equal to 1.2 Norwegian krona. Then you can just transform between units in a normal fashion. For example, you have that $1 is equal to 9 Swedish krona. And that in turn is equal to 1.2 Norwegian. Then you just have to multiply. So it's 9, 10.8. So you can count with currency just in the same way as you count with other units. Or here, for example, you can have 1 Norwegian krona. So you see here, just divide on both sides here. And you get how many dollars that is. So this many. This you can put on the calculator. And if you do that, roughly this. So this converting between currency is nothing special. You just use as any other unit you calculate with currency.